Board. All right. So I'm just going to start by talking about exam logistics and go through the notes, and then we'll do any questions. So for logistics, the exam is regular time, regular place on Wednesday of next week. You can bring a cheat sheet with whatever you want on it. In addition to that, you will be given the following equation sheet, which is on the practice exam or practice questions. This is not what the real exam will look like. It's way too many questions, but the equation sheet will look just like this. And so will all of the disclaimer stuff up above. The exam will be for the duration of class. It won't be extended, an extended period or anything, but depending on if the exam turns out to be too long, we'll make accommodations. But the intent is during that 55-minute time, there are probably going to be 12-ish questions, 12 to 14, maybe a little less, just depends. About a third tend to be conceptual, and the remaining two-thirds tend to be calculations. Sometimes one typical homework type question is broken up into 2 or 3 smaller questions, though, so don't let the number 12 to 14 scare you. It's not intended to be a long exam. All right. So I'm going to mainly focus on what's most important as far as calculations go. So I'll skip some conceptual stuff, and any questions on any of that I'm happy to answer, but just so you know the main calculation things, because that's a little bit harder to accommodate yourself to if you're not sure what to be trying to calculate. So the first calculational thing in chapter 18 is Coulomb's law. And so you can expect to find the net force on a charge due to 2 other charges. And these examples are kind of what I'm thinking of when I, excuse me, say that. So can you break forces into components and see how those components add up? And then once you've done that, apply Coulomb's law to figure out the size of your force magnitudes. That is pretty much the only calculation thing in chapter 18 other than seeing how much charge is on an object as far as how many electrons are missing or are present in abundance. And for that, it's just, let's see, we had that up here. Where'd that go? Huh. Maybe I didn't have it in this, but I think I had it in the homework. But it's just more or less the equation is Q equals NE, where the total charge is Q. E is the fundamental charge, 1.6 times 10 to the negative 19. N is the number of electrons. So if you're solving for N, you would say it's Q over E, and that will tell you how many electrons you have. That's how we got this as the number of electrons in 1 coulomb of charge. Chapter 18, calculation things are finding the size of an electric field. I would tend to lean more towards finding the size of an electric field due to a group of point charges, which would be questions like this one and the calculation version of this one that was in the homework. So again, finding the components of the electric field, then you can use Coulomb's law in the electric field form, which is this right here with absolute value, to find the magnitudes and get the overall or net electric field. It's still just the same vector math. The only new thing is for the magnitude of that vector, you use KQ over R squared. Okay. Moving right along. Oh, I was thinking of electric fields as a separate chapter. It's done that way in the calculus class. In this, we're still in chapter 18. Okay. All right, so as far as Gauss's law, finding the flux is not something I'm expecting you to do. So things like this are out of the question, as are how we found the field due to a sphere of charge and a capacitor. But applying the results of Gauss's law is something that can be expected, and something like this problem is a very typical one. It's on the practice questions as well. So if you're given a certain amount of charge sitting inside of a shell, can you figure out how much charge sits on the inside and outside of that shell? And that relies on both Gauss's law and the conservation of charge. That's about the calculation related stuff for chapter 18. For chapter 19, it would be conservation of energy to find the potential difference between 2 points, or otherwise, if you're given that potential difference, can you find how fast a charge is moving? So that would be these problems. You will not need to find the work done on a charge from these formulas at least. You would use the equipotential relationships. So I'll come back to that in a second. You will need to know how to find the potential due to a point charge so that you can find the total potential due to a group of point charges, which is where we come down here and just add up all the individual potentials. And so this question is a very good practice for that, to get used to the idea of, for once, you're not doing vector addition, and that's a nice thing. It's regular addition. What I mean for the equipotential way of computing work done is this formula. We use it in the form that the work done is negative Q times the change in potential. And so we had a sort of example of doing that right here, but in the practice exam, come over here. What I'm thinking of in my head when I say this is a question like this group of questions right here. So if you want to find how much work is required to move a charge from some point to another, only final and initial potential matter. So from B to A is how I would read this, and the work done as something moves from B to A is negative the value of our charge, which is the value of the charge itself is +6, but work itself is negative whatever the charge is times the change in electric potential. The final potential at A is 200 volts. The initial at B was 0 volts. And so this would be whatever this comes out to, -12 times 10 to the -4, or 1.2 times 10 to the -5, if I can do math. That may have gone the other way, but something along those lines. Let me see. That's 28. Okay, I was off by that factor. So from B to A, final minus initial. This must be the work we have to do. So that's why it's positive. And it was -3 because I just can't do math in my head very well, apparently. But that type of question of the work done by the electric field as a charge moves from one point to another is negative that charge times the change in potential if we're looking at the work done by the electric field. And that is what I would ask about, but this one is asking about the work done against the electric field. And that's like me having to lift the rock up versus gravity pulling it down. All right. Back over here. For capacitors, the main thing is just being able to calculate capacitance. So applying this to find the capacitance of a capacitor, and sometimes that would need to be done in combination with this right here, in the sense that you may be given the charge on the plates, and the voltage and maybe the plate spacing, and you want to find the area of the plates or something. You're given a few things and you got to find some other thing by putting these two formulas together. And then finding the energy stored. If there is a question like that, would be very straightforward. Just pick the one of these that is most relevant to what you're given. If you're given capacitance and voltage, use this one. If you're given charge and voltage, that one. If you're given charge and capacitance, use that one. These I would consider conceptual, where you insert a dielectric and you see what happens to the charge or potential, but you can do them with math. And if that way makes more sense to you, think of it as a calculation problem. But they will be multiple choice questions where it asks what happens. Okay, that's the main calculation stuff. And I think that is a good place to ask what your questions are about concepts or calculations.
Um, could we go over question number 13 on the exam repeat?
Yeah. 13. Okay. Two charges are located on the x-axis. We have Q1 is okay, it is labeled right. Sometimes I transfer these over and I mislabel things. I was a bit worried I did that here. Um, so Q1 6.7 times 10 to the negative 6 coulombs, and it is at 5.4 centimeters, 5.4 times 10 to the negative 2 meters. Q2 6.7, and it's at negative 5.4, and Q3 is 2.3, and that's it, plus 4.7, and Q4 is negative 7.3 at 6.9. See if I can squeeze that in somewhere. 6.9 centimeters. Find the magnitude and direction of the net electric field at the origin. Okay, so already I've made a mess of this, so let me, to get my vectors right, draw a little bit of a cleaner picture over here. Because to get the directions of my vectors correct, all I need to know is the signs of my charges. Negative, positive, positive, negative. And we're calling this one charge 2, this one charge 1, this charge 3, this charge 4. So at the origin, I got to look through all of these, see which way the electric field would point. So for charge 1, which way would it point?
To the left.
Mm-hmm. Yeah, it points away. And if it's not clear why, just think of we're really just picking out which of the electric field vectors around this charge are actually sitting at that origin point. What I mean by that is the overall electric field for this charge looks like this. But that means when we're over here to the left of it, that electric field points to the left. Okay. I'm going to take all but the one I need out. So now for charge 2, towards or away from charge 2?
Would it be away as well?
So what's the charge on charge 2, positive or negative?
Is it negative?
Mm-hmm. So it'll be towards it because the electric field lines point towards negative charges because that's the direction a positive test charge would feel a force. And that's saying this is part of the overall field surrounding the negative charge. Okay, what about charge 3?
go upwards. No, no,
Always think
no, it'll
about,
go down.
yeah, always think about you're standing at the point it's asking you about. We're standing at the origin and we're looking at that charge. Which way would we see the field point? We'd see it point kind of behind us, away from that charge. It says E3 and then E4.
Point upwards.
Mhm. Okay. So I need to find my net electric field, and that means I need my net X component of that field and my net Y component. I could do a table, but this one I think is pretty straightforward because we don't have stuff at an angle. So what would my net X component be in terms of E1 through E4? Charge 2. Oh, charge 2 was positive. I'm sorry. So this one is wrong. And if that's why you said it would point to the right, Tori, I apologize. Okay. All right, so that's fixed. Charge 2 was positive, and so its field points away from it. All right, so we need to find the net electric field in the X direction. So what would that be in terms of E1, E2, E3, and or E4?
So from this point on, are we just like adding?
Yeah, well, vector addition, yeah.
Hmm. So would you just start off with 6.7 times negative C?
Well, let's not do any numbers just yet. Just tell me in terms of E1, E2, E3, and E4.
Oh, what the signs are?
Uh-huh.
Okay, so E1 is negative.
So negative E1. Okay. What else?
E2 is positive.
Yeah, it points to the right. Anything else for the X components?
No, because the other two are going up and down.
Agreed. Yeah, so let's move on to the Y components and tell me about those.
E3 is going down.
Hmm. And E4.
E4 is going uh, up, so it'll be positive.
Hmm. Okay. If we leave it like that up until we get to this point, it becomes a lot easier to think about than trying to plug in everything and then figure out whether you do a positive or a negative. Now, to find the magnitudes of each of these fields, that's where I use KQ over R squared. So in the X direction, I have negative, and I need the field for E1. It's K Q1 over R1 squared, and then plus, and then the field for Q2. And then in the Y direction, I have negative K Q3 over R3 squared plus K Q4 over R4 squared. Okay, and then we can just put in Q1, Q2, Q3, Q4. What about R1, R2, R3, R4? What do I put for those?
Are the R's, I want to say the distance or
Hmm.
my, oh, okay. So centimeters on.
So it is the distance, but it's the distance between what and what?
The electron in the origin.
Yeah, between whichever charge we're looking at in the origin. So for charge one, how far is it from the origin?
Uh,
There are.
3 point. Oh, I can't see it. 5.4 centimeters.
Mhm. So 5.4 times 10 to the negative 2 meters is what's going to go right there. Okay. R2.
4 point. Wait, no, it's a negative 5.4.
Yeah, and I could leave in the negative because it'll get squared out anyway. So it won't affect anything, but R is just the distance. So we could throw the negative out as well. Okay. And R3.
4.7 centimeters.
Mhm. And then R4 would be that remaining one, 6.9 centimeters. Okay. If we put in all our numbers there, Q1, R1, Q2, R2, Q3, R3, and so on and so forth. It's a lot of calculation after that, but the hard work is done. And this would be probably at least 7 of the 10 points for a problem like this, because a problem like this tends to be something like 10, 12, 15 points because they take a lot of work. Um, but find the magnitude and direction is the last step. So once we get those numbers, whatever they turn out to be, my magnitude is just Pythagorean theorem because this is a vector quantity like any other. Really, the only thing we've done that isn't just regular vector math that we've done since physics one is this right here, and which way the fields point by figuring out whether they should point away or towards our charges. That's a new concept as well. Otherwise, it's just vector math. And for the angle, I like to ignore the signs of EX and EY, whatever they end up being, and then just figure it out based on my drawing. So once I figured out the number here and the number here, I would draw in a vector that had those components, meaning if this one's negative, I draw my vector to the left. If this one's positive, I draw it upwards. And that would let me figure out what angle it is that I just calculated by doing this at the bottom. Do y'all want me to calculate that, or is this okay? It's up to y'all.
I'm fine with this.
Okay. I don't mind calculating it either. I just, you know, want to be as time efficient as possible. Um, okay, other questions. Did this one make sense, Corey?
Yes, sir. Yes, sir.
Okay. Yeah, it's just a lot of steps. I don't think they're difficult. It's just when you put 5 or 6 or 7 steps of things together, it's hard to remember what comes after what.
Yeah.
Um, and really that can be a good thing to put on your cheat sheet is say, step one was label all your charges with a positive or negative. So I'll put that label positive or negative. Step two, draw vectors toward or away based on step one. And you want to do it so that their tails all sit at the point you're interested in. I didn't draw any of my vectors where it was pointing towards or away from the origin. I always drew them so that the tail was at the origin. Uh, Step three, um, find net x and y. And you do that by accounting for whether your components are pointing left or right. Um, I guess I should say for step three, though, if you need to find components of your field vectors themselves because they point at an angle, you need to do that as well. find components of E1, E2, and so on and so forth. And then you can find the net X and Y from that. Then your net field magnitude is Pythagorean theorem, and your angle is the inverse trig stuff. So yeah, it's a lot of straightforward steps, but they're hard to remember to do one after the other. And I could even add in a sub step of, man, I didn't think this through when I was labeling these. Let's call this step 4. This one would be step 3 because you got to do it before you can find the net X and Y. Then step 5 that I'm going to squeeze in is use electric field as KQ over R squared. Then I'd say step 6 is this. Apologize for how disorganized I apparently am today. Scooch this over so that's a little bit clearer. This off somewhere. I promise there's a method to my madness. This will come out somehow. That is gone. That is gone. Four away. Step 3 was find the components. So I'll scoop that back up here. It's gone. Step 4. We're almost out of the woods. Let's write that. Step 4 was find E net X and E net Y. Step 5 was use this. And step 6 was that right there. Ta-da! It's all fixed, sort of. So there's your 6-step process. Okay, other questions?
I like to give other people a chance.
Yeah,
Can we go and do 31?
yes. Okay. We have 2 parallel plates. The potentials between the 2 plates are V2 is 20 volts, and that's at 0.4 meters. V1 is 15 volts at 0.3 meters. We release an electron, and that part's not so important. To find the magnitude of the field, I'd say the easiest way is to use this right here. It's the thing that says the slope of the hill, the electric field, is equal to the change in height over the change in horizontal distance. So here, what's a little bit weird is we're not given the actual plate spacing. That's what would really be the distance d. But that's okay because the electric field is uniform between capacitor plates. And what that means is whether we calculate the slope or the potential difference over the entire plate spacing, or we just calculate the change in it over this distance, we'll get the same answer. And I'll show you that. I'll do both ways because we could see that this plate we're calling 0 volts anyway. All right, so if I use the numbers I'm given, this V always means higher minus lower potential. So I do 20 minus 15. And over the change in position, that's going to be 5 volts over 0.1 meters, or should be 50 volts per meter. Let me see if I didn't do anything too wild there. Yeah, volts per meter and newtons per coulomb are equivalent units. So either is fine. If I chose to do it with the actual plate voltages, or plate potentials is a better term there, I can still use this, but now my higher is 20, my lower is 0, and I'm looking over the distance from 0 meters, which would be one plate, to 0.4 meters, which is the other plate. And I would again get 20 over 0.4 is also 50 volts per meter. Right? Let me double check that. Yep. Okay, for the direction, I usually figure that out after. I figure it out before I find the magnitude, but I don't use this equation to get the electric field direction. Because there was that thing about you could use this one to figure out everything all at once, both the size and direction of the field. I prefer not to. I prefer to use this to find the size of the field and just always do larger minus smaller. And then for the direction of the field, we think about whether we're going from low to high or high to low potential. As we go from left to right, are we going from low to high or high to low?
Left to right, low to high.
So this plate is at the lower potential, this plate is at the higher potential. Which way does an electric field point? From low to high or high to low?
High to low.
High to low. So I know my electric field is to the left without ever doing really a calculation. And I prefer that. My stylus is having a little bit of trouble. And that makes sense because the electron is released from, or wait, let's see. I think this one is about if it goes towards the left or right plate. So we'd have to figure that out. Which one would it go towards?
I'm sorry, can you repeat the question?
Yeah, so we've got an electron that we've put in here, a negative charge. Would it go towards the right plate or towards the left plate from where it's sitting right now? There, my things are freezing up just a little bit on my end. I do not know why. See, drop it. There it is. Okay. Let me get this back open and it should be okay. All right, sorry for technical difficulties. So this electron right here, now that we know that the electric field points to the left, which way will the electron go from where it is right now?
Would it also go to the left?
Do electrons go with the electric field or opposite the electric field?
Opposite, opposite.
Opposite. So it'll go to the right. And So 32 says that you must decide which plate it hits. It's going to hit the right plate. And so if we wanted to figure out how fast it hits that plate, that in my brain jumps to conservation of energy. Can you think about hills and valleys? Yes, absolutely. So if we did it that way, we know that this side is at the higher potential. We're told it's 20 volts, and then this side is at least lower than that. We don't necessarily know it's 0 volts. I just kind of read that off the graph. But anyway, that would mean that as I go from the left plate to the right plate, I'm going uphill. And that is what electrons' negative charge naturally likes to do, which way it tends to accelerate. So that's another justification for why the electron would go to the right, because negative charges are weird and like to go uphill. Okay. If I wanted to find the speed, I'd use conservation of energy. So if the left plate is plate A and the right is plate B, I'd say 1/2 mVA squared plus the electric potential energy at A. I'm assuming there's no gravitational potential energy here because it doesn't tell me anything about the height of the electron off the ground, and it seems to stay at the same height anyway. Plus electric potential energy at B. I can see that the speed at, well, really, I should calculate from right here because that's where the electron's at rest. So I'll call that point A instead. In that case, we can say that at point A, the electron is at rest, and we know the electric potential energy can be written in terms of the electric potential. And what I want to find here is the speed as it hits the right plate. That's VB. And so I would solve for VB, little v, V. So this one's a big V. And that would end up being 2Q VA minus VB over mass, and I take a square root. I had to go through that step by step in my head to get to that right there. Let's check if it makes sense as far as the signs. Is VA or VB higher? Which one is at the higher potential, point A or point B?
Point A. I can't. Is it point A? The 20?
Um, Point A is where this electron is right now. Point B is the rightmost plate.
Right. No, point B.
Yeah, yeah. So point B is at the higher potential. That means that VA minus VB is going to be a negative number. And at first we'd say, uh-oh, I've got a square root of a negative. But then I remember that the charge that's moving as an electron, it's also negative, and those negatives will cancel. So I should get a positive number under my square root, and whatever it ends up being will give me the speed of this electron. So I would use 2. The electron charge is negative 1.6 times 10 to the negative 19. My potential difference, VA minus VB, would be 15 volts minus 20 volts, or in other words, negative 5 volts. And the mass of the electron is 9.11 times 10 to the negative 31 kilograms. If I take a square root of all of that, I'll get whatever the answer is. It seems it would be 1.33 times 10 to the 6 meters per second. Okay, other questions? I always say if you came to the review, you've got questions, so feel free to ask anything.
Final one for me. The question number 38.
Okay. Air-filled parallel plate capacitor is, yeah, I'm glad you asked about this one. This is the one where you're going to need to use both these things about a capacitor. Um, and I'll show you how I end up knowing that. So for one, as soon as I'm told something about a dielectric constant, this is the only equation that really tends to be relevant. So that one activates in my brain almost when I see kappa in my thing, or if I'm told dielectric constant, because they mean the same thing. Then I see the rest of the things that are in that formula. I see an area. I see a distance between my plates. How I know the other one comes in is it says something about charge. It's asking about that. That doesn't show up in this formula for a capacitor, but it shows up in this very common one. Now, it could have been that it told me something about electric potential energy and charge, and then I may not lean towards this one. I would lean towards probably this or this one. But I look at the other things I've got going on. I'm not told about energy, I'm told about electric potential. And so that is also in here. So how I put that all together is I want to know charge. I know that is capacitance times potential difference. Capacitance is this thing up here. These are the geometric properties of the capacitor. That's what capacitance depends on, not Q or V. It relates the two. So I put that in for my capacitance, and then I just say, all right, kappa is 1, no units. It's just a kind of scaling thing. Epsilon 0 is 8.85 times 10 to the negative 12 coulomb squared per meter squared. Area given. Plate spacing I'm given. And voltage I'm given is 12 volts or potential difference. Again, we've realized they are now more or less the same thing. Voltage is always higher minus lower potential. Potential difference can be lower minus higher if that's the way the charge went, but up to a negative sign, they're the same thing. That'll be whatever it ends up being. But these types of problems I would expect would be on this exam, and it's going to be given, I don't know, whatever 4 or 5 things, find the 6th or 7, I can't count right now. However many number of things, you're going to be given just enough to find the one extra thing you don't know. And it's just variations on that same theme.
Okay.
Yep. I will point out that that can mean a little bit more algebra than this one lets on, because say I were given everything but my distance between the plates. I might have to write distance is, I rearrange this, I solve it for distance. It's this, and then I'm given maybe charge and voltage, and capacitance can be written in terms of those, Q over V. But I say it doesn't depend on them because if I double Q, V doubles. But anyway, that would be over Q over V, or V kappa epsilon 0 A over Q. So sometimes they can be a little bit more algebra if you're given different things, but it's the same basic problem. Okay, other questions?
As far as conceptual questions, are there any specific topics we need to focus on?
Yeah, let's head back over here and let me take a look back through and point out some conceptual stuff. So, in these early parts, it's just the ways in which charging can happen, and that is through friction, contact, or induction. Friction, main thing is just knowing, all right, if this thing became positive, how did that happen? It's because that thing lost electrons. It did not gain positive charge because no positive charge can move. It lost electrons. Where did they go? To the other thing, and so the other thing would have become negatively charged. For induction, The main one that can kind of trick you with induction related questions is that it can happen even if one of the two objects is not charged. So we saw that with our aluminum can. I brought something charged up to it, a PVC pipe, and the aluminum can, even though it had no net charge on it, still felt a force, and it was an attractive force. Induction related forces are always attractive because of how the charge polarizes on the object. So an example of that would be, I think, the very first question in chapter 18. So it tells us some facts about these, and we can't always assume that attracts means one has some charge and the other has the same kind of charge. They have like charges. It could also mean induction has happened and they're attracted through that. So how we would figure it out for this one would be, okay, A attracts B and A repels C. That guarantees that A is charged because repulsion doesn't happen purely through induction. It also guarantees C is charged. So they have opposite, or I'm sorry, they have alike charges. A and C have like charges. So that could be both positive or both negative. I would then look at 2. Ball D attracts B, and D has no effect on E. That one is a little bit more unclear because of that induction thing. So maybe I'll jump to 3. A negatively charged rod attracts both A and E. So because it attracts A, I know for a fact that A is positive now because we said A must be charged and it's attracted by a negative rod, so A is positive. That also means that since it repels C, C is positive. It's possible that B is negative because A attracts it, but it could also be through induction. And let's see, a ball D attracts B, and D has no effect on E. So for that to be true, one or both ball D attracts B, D has no effect on E. So ball D could be positively charged, since we said B is potentially negative. But the no effect on E thing is the one I'd be a little bit concerned about. To me, that would indicate that neither D nor E is charged. Because if even one of them is charged, then Newton's third law says, okay, there has to be a force on either one from the other. Even though induction happens from one being charged and the other not, that doesn't mean that only the one that's charged attracts or repels. So, I think I'm down to that. And since ball D attracts B, and we said D is not charged, B must be the one that's charged, and that's an induction related process. So do I have plus, minus, plus, 0, 0? It looks like it's C. Is that ones? Okay. Yeah, so those are like almost a logic puzzle. Did all of that make sense? I can recap that.
It did for me.
Okay. All right, so that is a big one. And if that problem makes sense, I think you're good on this type of conceptual stuff. The next conceptual thing would be what an electric field is. It is defined as the force felt by a positive test charge divided by the size of that charge. That doesn't really give you a good sense of what it is, but that is how we measure it, and so that's how we choose to define it. What it is more or less the inherent push or pull that charges possess, independent of whether other charges are present around them. That's why I sometimes call it an aura, even though that word sounds a little bit too hand wavy. So something may ask you, for instance, I use one test charge to measure this electric field, and I find a certain measurement for that electric field. What if I used a test charge that was twice as large, meaning had twice as much charge? How would the electric field I measured change? Would it get bigger, smaller, stay the same? What do y'all think?
I'm sorry, I'm in the comment area. Can you repeat the question?
Yeah. So I want to measure an electric field, and so I use my test charge to do it. I use a certain value for the test charge, some number of coulombs or microcoulombs or whatever. I hold it up, I see what force is felt by it, and I use that to determine my electric field from this right here. If I decided to then retest with a new test charge that was twice as large, had twice as much charge to it, would I measure the same electric field, a weaker electric field, or a stronger electric field?
Would it be a weaker one? Well,
What
no, a
makes,
larger one due
Uh,
to how it's the
a sh-
size.
yeah. What were you going to say? I'm not sure who that was who was also saying something.
I was gonna say a stronger one.
Okay. So that means the electric field concept is still a little bit hazy because it doesn't depend on the test charge. It shouldn't matter what test charge I use. That's just an indirect way to get to it. And the formula says that much too, because even if I doubled the size of my charge, the force on it would double too. That leads to no change in the ratio of the two or the electric field. But that's getting across the concept that the electric field does not depend on the test charge. It depends on what you are testing, which would be whatever charge is creating that field. If I doubled that charge, then the electric field would change, but it does not change as a result of changing my test charge. I think. Okay, I didn't have one like that, but that just knowing the electric field is independent of what test charge you use. It's just a property of whatever's creating it is important. Um, the direction of the electric field, so away from positive towards negative, and which way other charges feel a force when placed in that electric field. And that would be along the direction of the field for positive charges, opposite the direction of the field for negative charges. What else concepts? This is still direction. Field lines. If there is a question on field lines, it would be rare, but it's that they point away from positive toward negative, and that the strength of the field is indicated by how close together the lines are. So the field is stronger where they're closer together. Capacitors have a uniform field. I can't say there's much conceptual on Gauss's law other than what does it say? It says that the amount of field lines leaving a surface tell you about the charge inside the surface. Properties of conductors is not heavily emphasized. For potential, just remembering the hill analogy. Potential is the height of the hill. Electric field is the slope of the hill. And so the pull of the electric field for positive charges is down the hill, and that's the direction the electric field points. The pull for negative charges is up the hill, opposite the direction of the field. And so we summarize that as positive charges roll downhill, negative charges roll uphill. Other conceptual stuff I can't really think of other than I would just look at this to make sure the distinction between those four main things we've looked at is clear. And then other conceptual would be equipotential surfaces. That work is only done when you move between equipotential surfaces, not along the same one, or you just happen to end up back on the same one you started on. Work is not done then. And for capacitors, there can be some conceptual stuff, and that's you insert a dielectric while the battery is connected or while it is not connected, and see what happens to either the charge or the voltage on the plates. We know indefinitely, like it doesn't matter what we've done. As long as we insert a dielectric, the capacitance does increase. But if we don't do anything to the capacitor as far as inserting a dielectric, changing its plate area, or changing the spacing between the plates, we cannot change capacitance. So don't let the change charge, change voltage thing confuse you. That does not affect the capacitance because it's a property of the plates themselves. And that doesn't change just because you put more charge on the plates. And that's what these examples are talking about. I think that is the main things I would call concept stuff. Are there other questions? Okay, if not, we can call it a day. And I'll have this posted, but really, I'm happy to answer anything. I got whatever time is needed. Okay. All right. Well, we'll call it a day, and I will see you all on Monday. The exam is Wednesday, not Monday, but if you have questions, just email me, and we will take a look at any other things that come up. All right. Y'all enjoy your weekend.
Have a good day.
You too.
You too.